The important addition to the amplifier shown in the previous video, which makes it stable, is the emitter resistor Re. This adds what is known as negative feedback to the circuit. We'll look at what this means in more detail later, but for now, a simple explanation will suffice. Feedback is when we take some of the output of a system and feed it back into the input. Positive feedback adds this sampled output signal to the input, making the input bigger. This tends to destabilize the system. Negative feedback, on the other hand, subtracts the sample output from the input, making it smaller, and this tends to stabilize the circuit and has other benefits which we'll describe later. The emitter resistor adds negative feedback to the circuit, and this works in the manner shown in the diagram on the screen. When a voltage to be amplified, Vin, is applied to the amplifier, this causes a current to flow through the transistor as normal. The current flowing through the transistor causes a voltage across VE, which in the diagram I've labelled the feedback voltage VF. But it's the actual signal voltage VBE going into the transistor between the base and the emitter which has really been amplified. And you can see from the diagram that VBE is equal to Vin minus Vf. So the voltage across the emitter resistor is opposing or subtracting from the input voltage, and this is what is causing the negative feedback. We can now see simply how this can prevent thermal runaway. If a transistor were to get hot and more current were to flow, this would increase Vf and lower the input, which stabilizes the whole system, because the lower input will lead to less current flowing. This is a good illustration of how negative feedback tends to stabilize things in a circuit. Another benefit is also obtained from adding Re, and this is that it allows us to set the transistor current without having to worry about beta, the current gain, which you might remember I said previously varies between different batches of transistor. If we use a potential divider to set VB to a particular voltage, then because the base emitter junction is a diode, VE must equal VB minus 0.7. However, since the bottom of Re is at 0 volts, and the top is now at a fixed voltage, VB minus 0.7, a current flows, which is equal to VE divided by Re. And this current has to come from IC, or IE. And so we can set IE for the whole transistor like this, without having to use beta in our calculations. When we design the potential divider to fix a base voltage, we need to ensure that the current going through the divider, which I've labelled ID in the diagram, is much more than any current which is sucked into the base, IB, as shown on the diagram. This makes sure that IB does not affect the voltage VB. This is why in the design which I did in the previous video, I chose R2 to be 10 times Re, because this makes sure that there's plenty of current in the divider. If we want to be more accurate, however, there is a better way of designing a divider, which will give a higher input impedance to the amplifier. Often, when we look at a data sheet, it will give a value for the worst possible value of beta. In other words, the lowest value that beta could be. And this gives us a way of calculating the worst possible value of IB, because IB is equal to IC divided by beta. So we can just choose ID, the current going through the voltage divider, to be, say, 10 times bigger than the worst case for IB, which comes from the worst case for beta for the transistor, and then calculate R1 and R2 using this current. This usually gives a better design than just using the simple rule of thumb that R2 is equal to 10 times Re, as we did in the previous example.